Membrane technology covers all engineering approaches for the transport of substances between two fractions with the help of permeable membranes. In general, mechanical separation processes for separating gaseous or liquid streams use membrane technology. Applications: membrane separation processes operate without heating and therefore use less energy than conventional thermal separation processes such as distillation, sublimation or crystallization. The separation process is purely physical and both fractions can be used. Cold separation using membrane technology is widely used in the food technology, biotechnology and pharmaceutical industries. Furthermore, using membranes enables separations to take place that would be impossible using thermal separation methods. For example, it is impossible to separate the constituents of azeotropic liquids or solutes which form isomorphic crystals by distillation or recrystallization, but such separations can be achieved using membrane technology. Depending on the type of membrane, the selective separation of certain individual substances or substance mixtures is possible. Important technical applications include the production of drinking water by reverse osmosis, filtrations in the food industry, the recovery of organic vapors such as petrochemical vapor recovery and the electrolysis for chlorine production. In wastewater treatment, membrane technology is becoming increasingly important. With the help of ultramicrofiltration it is possible to remove particles, colloids and macromolecules, so that wastewater can be disinfected in this way. This is needed if wastewater is discharged into sensitive waters, especially those designated for contact water sports and recreation. About half of the market is in medical applications such as use in artificial kidneys to remove toxic substances by hemodialysis and as artificial lung for bubble-free supply of oxygen in the blood. The importance of membrane technology is growing in the field of environmental protection. Even in modern energy recovery techniques, membranes are increasingly used, for example in fuel cells and in osmotic power plants. Current market and forecast: the global demand for membrane modules was estimated at approximately $15.6 billion in 2012. Driven by new developments and innovations in material science and process technologies, global increasing demands, new applications, and others, the market is expected to grow around 8% annually in the next years. It is forecast to increase to $21.22 billion in 2016 and reach $25 billion in 2018. Mass transfer: two basic models can be distinguished for mass transfer through the membrane, the solution diffusion model and the hydrodynamic model. In real membranes, these two transport mechanisms certainly occur side by side, especially during ultrafiltration. Solution diffusion model equals, in the solution diffusion model, transport occurs only by diffusion. The component that needs to be transported must first be dissolved in the membrane. The general approach of the solution diffusion model is to assume that the chemical potential of the feed and permeate fluids are in equilibrium with the adjacent membrane surfaces such that appropriate expressions for the chemical potential in the fluid and membrane phases can be equated at the solution-membrane interface. This principle is more important for dense membranes without natural pores such as those used for reverse osmosis and in fuel cells. During the filtration process, a boundary layer forms on the membrane. This concentration gradient is created by molecules which cannot pass through the membrane. The effect is referred as concentration polarization and, occurring during the filtration, leads to a reduced transmembrane flow. Concentration polarization is, in principle, reversible by cleaning the membrane, which results in the initial flux being almost totally restored. Using a tangential flow to the membrane can also minimize concentration polarization. Hydrodynamic model equals, transport through pores in the simplest case is done convectively. This requires the size of the pores to be smaller than the diameter of the two separate components. Membranes which function according to this principle are used mainly in micro and ultrafiltration. They are used to separate macromolecules from solutions, colloids from a dispersion or remove bacteria. During this process the not-passing particles or molecules form a pulpy mass on the membrane, and this blockage of the membrane hampers the filtration. This blockage can be reduced by the use of the cross-flow method. Here, the liquid to be filtered flows along the front of the membrane and is separated by the pressure difference between the front and back of the membrane into retentate on the front and permeate on the back. The tangential flow on the front creates a shear stress that cracks the filter cake and reduces the fouling. Membrane operations. According to the driving force of the operation, it is possible to distinguish pressure-driven operations, microfiltration, ultrafiltration, nanofiltration, reverse osmosis. Concentration-driven operations, dialysis, pervaporation, forward osmosis, artificial lung, gas separation. Operations in an electric potential gradient, electrodialysis, membrane electrolysis, for example chloralkali process, electrodeionization, electrofiltration, fuel cell. Operations in a temperature gradient, membrane distillation. Membrane shapes and flow geometries. There are two main flow configurations of membrane processes, cross-flow tangential flow and dead-end filtrations. In cross-flow filtration, the feed flow is tangential to the surface of membrane, retentate is removed from the same side further downstream, whereas the permeate flow is tracked on the other side. In dead-end filtration, the direction of the fluid flow is normal to the membrane surface. Both flow geometries offer some advantages and disadvantages. Generally, dead-end filtration is used for feasibility studies on a laboratory scale. The dead-end membranes are relatively easy to fabricate, which reduces the cost of the separation process. The dead-end membrane separation process is easy to implement and the process is usually cheaper than cross-flow membrane filtration. The dead-end filtration process is usually a batch-type process, where the filtering solution is loaded into the membrane device, which then allows passage of some particles subject to the driving force. The main disadvantage of a dead-end filtration is the extensive membrane fouling and concentration polarization. The fouling is usually induced faster at higher driving forces. Membrane fouling and particle retention in a feed solution also builds up a concentration gradients and particle backflow. The tangential flow devices are more cost and labor-intensive, but they are less susceptible to fouling due to the sweeping effects and high shear rates of the passing flow. The most commonly used synthetic membrane devices are flat sheets plates, spiral wounds, and hollow fibers. Flat plates are usually constructed as circular thin flat membrane surfaces to be used in dead-end geometry modules. Spiral wounds are constructed from similar flat membranes but in the form of AA-OE pocket R- containing two membrane sheets separated by a highly porous support plate. Several such pockets are then wound around a tube to create a tangential flow geometry and to reduce membrane fouling. Hollow fiber modules consist of an assembly of self-supporting fibers with dense skin separation layers, and a more open matrix helping to withstand pressure gradients and maintain structural integrity. The hollow fiber modules can contain up to 10,000 fibers ranging from 200 to 2500 I1/4 m in diameter. The main advantage of hollow fiber modules is very large surface area within an enclosed volume, increasing the efficiency of the separation process. Membrane performance and governing equations. The selection of synthetic membranes for a targeted separation process is usually based on few requirements. Membranes have to provide enough mass transfer area to process large amounts of feed stream. The selected membrane has to have high selectivity properties for certain particles. It has to resist fouling and to have high mechanical stability. It also needs to be reproducible and to have low manufacturing costs. The main modeling equation for the dead-end filtration at constant pressure drop is represented by Darcy unregistered trademark S law, where Vp and Q are the volume of the permeate and its volumetric flow rate respectively. I1/4 is dynamic viscosity of permeating fluid, A is membrane area, Rm and are other respective resistances of membrane and growing deposit of the foulants. Rm can be interpreted as a membrane resistance to the solvent permeation. This resistance is a membrane intrinsic property and is expected to be fairly constant and independent of the driving force, Ip. R is related to the type of membrane foulant, its concentration in the filtering solution, and the nature of foulant-membrane interactions. Dacia Euro unregistered trademark S law allows for calculation of the membrane area for a targeted separation at given conditions. The solute sieving coefficient is defined by the equation, where Cf and Cp are the solute concentrations in feed and permeate respectively. Hydraulic permeability is defined as the inverse of resistance and is represented by the equation, where J is the permeate flux, which is the volumetric flow rate per unit of membrane area. The solute sieving coefficient and hydraulic permeability allow the quick assessment of the synthetic membrane performance. Membrane separation processes have a very important role in the separation industry. Nevertheless, they were not considered technically important until the mid-1970s. Membrane separation processes differ based on separation mechanisms and size of the separated particles. The widely used membrane processes include microfiltration, ultrafiltration, nanofiltration, reverse osmosis, electrolysis, dialysis, electrolysis, gas separation, vapor permeation, pervaporation, membrane distillation, and membrane contactors. All processes except for pervaporation involve no phase change. All processes except dialysis are pressure-driven. Microfiltration and ultrafiltration is widely used in food and beverage processing, biotechnological applications and pharmaceutical industry, water purification and wastewater treatment, the microelectronics industry, and others. Nanofiltration and reverse osmosis membranes are mainly used for water purification purposes. Dense membranes are utilized for gas separations and sometimes in membrane distillation. The latter process helps in the separation of azeotropic compositions, reducing the costs of distillation processes. Pore size and selectivity. The pore sizes of technical membranes are specified differently depending on the manufacturer. One common distinction is binominal pore size. It describes the maximum pore size distribution and gives only vague information about the retention capacity of a membrane. The exclusion limit or cutoff of the membrane is usually specified in the form of NMWC. It is defined as the minimum molecular weight of a globular molecule that is retained to 90% by the membrane. The cutoff, depending on the method, can be converted to so-called D90, which is then expressed in a metric unit. In practice, the MWCO of the membrane should be at least 20% lower than the molecular weight of the molecule that is to be separated. Filter membranes are divided into four classes according to pore size. The form and shape of the membrane pores are highly dependent on the manufacturing process and are often difficult to specify. Therefore, for characterization, test filtrations are carried out in the pore diameter refers to the diameter of the smallest particles which could not pass through the membrane. The rejection can be determined in various ways and provides an indirect measurement of the pore size. One possibility is the filtration of macromolecules, another is measurement of the cutoff by gel permeation chromatography. These methods are used mainly to measure membranes for ultrafiltration applications. Another testing method is the filtration of particles with defined size and their measurement with a particle sizer or by laser-induced breakdown spectroscopy. A vivid characterization is to measure the rejection of dextran blue or other colored molecules. The retention of bacteriophage in bacteria, the so-called bacteria challenge test, can also provide information about the pore size. To determine the pore diameter, physical methods such as porosimetry are also used, but a certain form of the pores is assumed. Such methods are used for membranes whose pore geometry does not match the ideal, and we get nominal pore diameter, which characterizes the membrane, but does not necessarily reflect its actual filtration behavior and selectivity. The selectivity is highly dependent on the separation process, the composition of the membrane and its electrochemical properties in addition to the pore size. With high selectivity, isotopes can be enriched in nuclear engineering or industrial gases like nitrogen can be recovered. Ideally, even racemics can be enriched with a suitable membrane. When choosing membrane, selectivity has priority over a high permeability, as low flows can easily be offset by increasing the filter surface with a modular structure. In gas phase filtration, different deposition mechanisms are operative, so that particles having sizes below the pore size of the membrane can be retained as well. See also, artificial membrane, particle deposition. Notes. References, Osada, Y., Nakagawa, T., Membrane Science and Technology, New York, Marcel Decker, Incorporated, 1992. Zeman, Leos J., Zidny, Andrew L., Microfiltration and Ultrafiltration, Principles and Applications, New York, Marcel Decker, Incorporated, 1996. Mulder M., Basic Principles of Membrane Technology, Kluwer Academic Publishers, Netherlands, 1996. Chornitz, Maek W., Sterile Filtration, Springer, Germany, 2006, Van Raesar, Zidny A. Bioprocess Membrane Technology. J. Memsci 297, 2007, 16-50. Templin T., Johnston D., Singh V., Tumbleson M. E., Belle R. L. Rausch K. D. Membrane Separation of Solids from Korn Processing Streams. Biostech 97, 2006, 1536-1545. Ripger S., Schultz G. Microporous Membranes in Biotechnical Applications. Bioprocess N1, 1986, 43-49. Thomas Mellin, Robert Rothenbach, Membranverfahren, Springer, Germany, 2007, ISBN 3-540-00071-2. Munier-Kerian, Handbuch Ultrafiltration, Beer, 1990, ISBN 3-90256673-87-3. Aberard Stored, Membranen und Membranprozess, VCH, 1992, ISBN 3-527-28041-3.